Hi, and welcome to 3.1 Free Fall Down. So, what happens when you fall down in a gravitational field? Students will be able to calculate and fully describe the motion of a freely falling object. I like to start the discussion of freely falling objects by posing the classic question, which will fall first, a hammer or a feather in a gravitational field? But the caveat to this is you neglect air resistance. So if you can neglect air resistance, normally we think of a falling feather as like floating down. What would happen if there was no air? Well, in this video from NASA, they actually did that experiment on the moon, and I highly recommend that you watch it. I tried to embed the video and record this PowerPoint with it playing. It didn't really work out. All of these videos talk about that question. They're going to be linked in the green extension video folder in Schoology. This will be the first one linked there. There's a lot of videos about this question. And it doesn't have to be a hammer and a feather. You could do this experiment at home with a heavy object and a very light object, like let's say a piece of paper. But to get around the air resistance thing, crumble up the piece of paper as tight as you can so there's not as much surface area for the air to slow it down. And which would land first? Let's say like a textbook and a crumpled up piece of paper and drop them at the same time and see what'll happen. Don't drop them on your foot or anything because that would hurt. So when talking about freely falling objects, we have to talk about the acceleration due to gravity. An object accelerates at a constant rate near the surface of a planet because of the planet's gravitational pull. And in all of these problems, we're going to be neglecting air resistance. When you take AP physics, there's actually a drag force equation where you could calculate it's actually a frictional force that air resistance is exerting on the falling object. But we'll neglect all that and just keep it simple and pretend like there's no air resistance. You're going to accelerate towards the ground at a constant rate. That doesn't mean you move with a constant velocity towards the ground. You're accelerating at a constant rate, which means that your velocity gets faster and faster as you fall. The acceleration due to gravity is represented either by, you could call it like A sub g, but this is such an important quantity that they give it its own little thing. Little g is the acceleration due to gravity. On your reference table, it's known as negative 9.81 meters per second squared. Pause the video here and think about why is it negative? Why would we make that acceleration due to gravity negative? Pause the video, think about it. Well, you're accelerating towards the ground if it's a falling object, and down, see that vector I just drew? Down is the negative direction. So your acceleration points in the negative down direction. So it's important that we remember that the acceleration due to gravity is negative. Now, if you look in your reference table, they give it to the hundredths place. I typically always use to the tenths place, so negative 9.8 meters per second squared. Get used to writing that. But don't get too used to writing it because if you take AP physics next year, you could just use good old negative 10. And you have so many other physics things to worry about. You don't have to get bogged down in the nearest tenths place. It gets like so crazy after that that they just like, well, let's make our life a little bit easier and just say it's 10 instead of 9.8, but I like 9.8. So where is this value? Do you have to memorize it? No, you do not. Look at your reference table, try to find where is the value for acceleration due to gravity found on your reference table. Look for it now. If you're not looking for it, then you're going to forget. You got to do the work first before I give away the answer. If you do the work, then you're more likely to remember the thing. So it is on the front page in the list of physical constants. Anytime you're looking for a number, look over here. And acceleration due to gravity is the second thing given there. As I said, it's given as 9.81 in the nearest hundredths, but they just give you the magnitude of all these numbers. So you have to remember to make that negative. If you want, you can, if you have a printed out reference table, you could draw in a negative right there. Okay. So before we do some word problems, I do like to talk about some free fall vocabulary. Free fall is the motion of a body when only the force due to gravity is acting on the body. We're going to talk about free body diagrams a little bit later. Looks something like this. You only have the force due to gravity and you neglect, there is no air resistance here. So freely falling means there's no air resistance. Speaking of free body diagrams, some physics teachers teach forces first, like this is a force vector. But we'll just take it at face value for now and just recognize that, okay, if an object's falling, it is accelerating downward. And we talked about acceleration already, so we can do some problems with that. But then when we do dynamics, we're like, well, why is it accelerating downward? But we'll just accept that it's negative 9.8 meters per second squared for now. Air resistance is a special type of frictional force that acts upon objects by opposing their motion as they travel through the air. So if you're falling down, your air resistance is moving against that motion. It's a frictional force. Terminal velocity is the constant speed that a freely falling object eventually reaches when the air resistance of the medium through which it is falling prevents further acceleration. So if we had that free body diagram again, you're falling because the force due to gravity is pulling you down. And if you didn't neglect air resistance, then yeah, you could put in a little bit force due to air. It doesn't say fair, it's F sub air. And what happens with the air resistance, and like I mentioned before, when you take AP physics, there's this drag force equation. The magnitude of the air resistance is dependent on the velocity through which you're moving through the air or the fluid. So the faster you go, the larger this air resistance force becomes until you reach a point where the air resistance, the magnitude of the air resistance is equal to the magnitude of the force due to gravity. And when those two forces are balancing each other out, you actually don't accelerate anymore. You're reaching your terminal velocity. You're still moving downward, but you're moving downward with a constant velocity now. And you can't get any faster than that unless somebody like came behind you and gave you a push as you were falling down, which wouldn't happen. So there is some cool skydiving videos. If you have the time, I highly recommend you checking them out. They are in the green extension folder as well. You might recognize the person doing the skydiving. So word problem vocabulary. We're about to do a word problem, and there are some key terms that you should look for as you read these problems, because they're going to tell you what numbers you can plug in to the equation. Everybody likes just plugging in the numbers into the equation, right? Well, sometimes the numbers specifically aren't given to you. They'll say some words instead. So here are some key words to look out for. At rest. What do you think that's telling us? What can we plug in on our given information? If it's at rest, that means the initial velocity is 0. And if it comes to a stop, that means the final velocity is 0. We knew those from our kinematics 1, the unit 2 stuff. Now we're going to encounter words that say like it's dropped, the object is dropped, or they could say it's dropped from rest, but if they just say you're dropping a ball, okay, then that's telling you the initial velocity is 0. You're just holding it there, the velocity is 0, and then you drop it. So they're telling you you could plug this in to your equation. And if it's falling, they don't have to say it falls freely. So if it's an object that falls, then we assume that it's negative 9.8 meters per second squared. That's the acceleration. So you could write g. Technically, that would be cool to do, but don't forget that's really a. In our kinematic equations, they all have a. We have vf, vi, d, t, and a, which now the acceleration due to gravity can plug in over there. So let's do an example, and everybody needs to stop because it's hammer time.
Can't touch this. Break it down.
That's right. A hammer is dropped from the top of a building undergoing construction. Now, it looks like they didn't tell you any numbers in that sentence, but they did because it says it's being dropped. So not only does that tell us the initial velocity is 0 meters per second, But since there's a building there, we can assume we're on planet Earth. And actually, you always assume you're on planet Earth unless the problem tells you otherwise, which it will. There'll be problems where they're like, you're on planet X, and you don't know what the acceleration due to gravity is. But in this case, we can assume that we're on Earth, so we know the acceleration is negative 9.8 meters per second squared. And you know what? It's actually a good idea to just draw a picture sometimes to start out. So the ball is there, your initial velocity is 0 meters per second, and you're going downward. And the time it takes, they tell you, is 5 seconds. So actually, if you drop something and you count the seconds that it takes, you could estimate, you get a pretty good estimate for the height that you're dropping it from. Now, the height that we're going to calculate, that's what they're looking for, the displacement. It's going to be negative because we started at the top and we moved downward. We had a negative displacement. So the answer will pop out a negative number, but if they're asking for the height of a building, you could just make it positive and be like, well, I did the kinematic equation. I know how far the thing dropped, so that building must be this tall. So without any further ado, let's do the thing. We don't have VF, so you look in your reference table for the equation without VF, just like we've been doing, and you know that it's D equals VIT plus 1/2 AT squared. Now you can plug in, and some teachers just go, okay, VI 0, boom, that's totally fine, and then you could write 1/2 negative 9.8 T squared. And actually, since you know this is 0, and you're going to be doing 1/2 times the acceleration due to gravity a lot. All right, so some teachers make their own equation and they're like, boom, negative 4.9, because that's always going to be half of 9.8 T squared. And the teachers are like, hey, that's a cool equation for figuring out the height of a dropped object. But that only works if it's at rest and if you're on Earth. And it's not given to you. This isn't given to you in your reference table. So I will always revert back to the reference table just because it's a good jumping off point for everybody. It's all common ground. And I'll always plug in pretty much, even though it's just going to be boom, I'll plug it in over there just to go through the same process. If you have a consistent process, these problems become a lot easier. There's less guesswork. You don't have to think on your feet as much and potentially make mistakes. If you just do the thing the same way every single time, then you're more consistent. So you get a displacement of negative 122.5 meters. And some students, rightfully so, are like, hold on, Mr. Nangle. They're saying, what's the height of the building? And I have never described the building as being negative 100 meters tall before. So this is just a math equation. It's going to pop out a number based on the parameters that you give it. And we're saying you're accelerating downward, not upward. So like I said before, your displacement is downward. If you wanted to be specific, you could say in your answer, oh, the height of the building is 122.5 meters. If you don't make it positive in this type of question where they're asking for the height of the building, that's fine. You could just leave it like that. I'm not going to take off points because you did the physics and I know that you know what the right answer is. Okay, now part B can be a little bit confusing. I'll erase the part A stuff and we'll talk about part B. So part B says, what is the velocity of the hammer when it hits the ground? In other words, they're really looking for the final velocity. This is what we're going to solve for. And we know now that this is negative 122.5. You keep that negative because we're still going downward. Our displacement is negative. Another way I could have worded this is, like I said, what is the final velocity? And here's where the confusion comes in, because we've experienced things dropping and hitting the floor before. And if you're picturing that in your mind, that's awesome. But the problem people run into is, okay, here's this thing, it drops, it hits the ground, and then it's at rest again, right? So does that mean the final velocity is 0? Because it hits the ground and stops. The ground stops it, right? Does it come to a stop like we said before? No, that is not the right way to think about this. What we're saying is, yeah, you're starting from rest, but then you're accelerating and you're getting faster and faster and faster, and then smack, you hit the ground with some final velocity. How fast are you going when you hit the ground? That's the better way to ask it, I guess. Instead of saying, Well, I mean, this is still technically true. What is the final velocity? But it's a little misleading because, like I said, some people are like, well, it hits the ground and comes to a stop. So the final velocity is zero. But you do hit the ground with some velocity, and that's what they're looking for. If you said the final velocity is 0 meters per second, then the math thinks that you're okay. The initial velocity is zero, the final velocity is zero, so you must be moving at a constant velocity of zero. Did you not change your velocity at all? The math is just going to take what you put in, negative 9.8 meters per second squared, and it'll pop out so you're starting from rest and getting faster in the negative direction. So it will give you a number, and that's how fast you're hitting the ground with. So that's my little side explanation about that, because I know a lot of people have a question about that when they first see these types of problems. But back to the kinematic equations. We have 4 pieces of information now. We could actually use a couple different formulas. When I have a choice, I try to use the information that they give us, just in case I made a mistake or in case there's a rounded answer in the thing that I calculated. So we're going to find an equation without displacement, and that's going to be just the normal VF equals VI plus AT. So we're looking for the final velocity. We're dropped from rest, so this is 0 meters per second, and we're accelerating at negative 9.8 meters per second squared for 5 seconds. And 9.8 times 5 is another number that you'll be doing a lot. 9.8 times 5 gives you 49 meters per second in the negative direction. So when you hit the ground, you're moving with a velocity of 49 meters per second after falling for 5 seconds. So I wouldn't want to be under that hammer after it's been dropped 122.5 meters because it's moving at 49 meters per second. All right, time for you to do some practice. If you want, you could pause the video, read the problem, try to do the calculation, and then watch along with me and see if you got it right. So you pause the video now, do the problem. All right, now hopefully you're playing it. You are a roadie for your favorite band, Fizz X. As you move equipment around, you go to put the bass guitar in. Suddenly, you drop the bass. The bass drops a distance of 5 meters from the stage to the floor below. What is the final velocity and how many seconds does it take for the bass to drop? So again, you're dropping things. I could underline, it says it a lot. That tells you the initial velocity is 0 meters per second. And we're assuming that you're on planet Earth, so it's negative 9.8 meters per second squared. That's the acceleration. And they're telling you now the displacement is 5 meters. So they're looking for the final velocity. And you could draw yourself a picture too at this point. We're going to be doing projectile motion problems in a few lessons, and it really helps to draw pictures when doing that. You're just dropping it, so it's nothing too crazy right now, but it helps organize your thoughts for some people. And you could even say, oh, okay, I know this distance is 5 meters. And by drawing the picture, I realized, my displacement is downward. So I want to make sure I make the displacement negative to agree with my negative acceleration. So you're looking for the final velocity. They don't tell you the time, and at this point we're not looking for it. So the equation without time is equal to VF squared equals VI squared plus 2AD. So then you can plug in VF squared equals, this is 0 squared, so you could just cross that out if you want. 2 times negative 9.8, that's 19.6. You're going to be doing that a lot. So negative 19.6 times negative 5. So VF squared is equal to 98. And what you want to do at this point, 2 times 5 is 10. 10 times 9.8 is 98. What you want to do now is take the square root. Okay, and when you're taking the square root, you're actually going to get 2 different answers. You could either get positive 9.899. That's a long decimal. We'll just call it positive 9.9 meters per second. Or don't forget, negative 9.899 times negative 9.899 will still get you positive 98. So this, when you take the square root, you could still get a negative number. You choose to make it positive or negative. Well, why would I choose to make it negative 9.9? Because your final velocity is downwards. The direction of this vector is down 9.9 meters per second in the downward direction. So yeah, when I'm doing that square root, I want to make sure I make it negative 9.9 meters per second. So it agrees with all the other signs that I've been doing. So I'll erase this stuff and we'll do part B, which asks you to find the time. So if we're looking for the time, and in this case, we definitely rounded this number. So I'm actually going to use VI, A, D, and T and find an equation without VF because we rounded that, which is D equals VIT plus 1/2 AT squared. You plug in your numbers. VI is 0, so that's cool. We're looking for T plus 1/2 times negative 9.8 times T squared. And if VI isn't 0, let's say you throw the thing downward or throw it upward, that means you have a T term and a T squared term. And if you were solving for T, do you know what you would have to do? You'd have to do the quadratic formula to find the time. So that is fair game in this class. You got to do that whole negative b plus or minus the square root of b squared minus 4ac over 2a. But not in this case because vi is 0. So if they say it's dropped, then you're like, okay, sweet. Vi is 0. I like that. So you're going to solve for t. You get negative 5 is equal to negative 4.9. Like I said, you're going to be doing 1/2 times negative 9.8 a lot, and you'll end up just memorizing it just because. So you divide, and you get t squared is equal to 1.02, and then you could do second square root second answer in your calculator because this is a longer decimal. So some people don't know that you could do the second answer thing. It's typically above the negative sign. So if you look at the second function, so you do second square root, second answer, and then it'll give you a more precise answer, 1.01 seconds. Okay. And, that's about it. We're just dropping objects in a gravitational field, and they're accelerating downward at negative 9.8. That's the main takeaway is now we have some hidden information in the problems where we're dropping it. We know the acceleration, and since it's being dropped, the initial velocity as well is 0. Tricky stuff. And that's about it. Thanks for watching, and have a great day.